Okay. Should I start? Fine. I'll start. Welcome, guys. Welcome to the session for the solution part of GATE 2003 Mechanical. And I'm going to discuss the manufacturing materials and industrial engineering part. And we have good questions. Some are easy, some are little, tricky, where you have to keep some thoughts and you have to solve the questions. And let's start. So this is my intro. Anyways, let's skip this. So the first question. So in the first question, this is 1 mark question, of course. And in the if you have attended our classes, we have clearly mentioned this is one of the important questions. Even in assignments, also we have given this question as the following. But here they were asking which one of the following is true. It's an easy, very easy question. If you remember, where sorry, 1 minute, guys. Yeah. So if you remember, we have seen that in AOQ, in inventory control, the total cost, right? The total cost is equal to right? Purchase cost, right? Purchase cost. This is what we have seen, right? Purchase cost plus holding cost, or I can say ordering cost, right? Ordering cost. And the last one was holding or carrying cost. Holding or carrying cost. Good. So in purchase cost, we were writing this as PC, and this we were writing as OC, this we were writing as CC or HC, right? And each of it, so this purchase cost was some constant. We have put this as constant, that's fine, right? And we know that ordering cost, OC, is equal to ordering cost, or I can say, that it is number of orders into ordering cost per order, right? And number of orders we have written as D by Q into C naught. In the same way, holding cost or carrying cost we have written as average inventory Q by 2 into CC. That's it. And with this, we can solve this question, right? How? See here. So if you see here, with reference to the economic quantity, which one of the following options are correct? So let's not see the options. First, we'll decide what are the curves, and then we'll go to these options, and then we'll select whichever is appropriately correct. Good. So here, if you have seen, the curve is, there are 4 curves, and x-axis we have order quantity, and that order quantity is represented by Q, and cost is represented by total cost, or C, whatever it is there. We can write as cost in rupees, whatever it is there, right? Good. Now, so the cost is depending upon quantity Q. That is what you have to understand here. Good. So here, if you see in this figure, the curve P1 is coming down and going up. Okay, let's say that, okay, we do not know what is that. Forget. Let's go to curve 2, P2. What is P2? I can say it is linearly increasing as the order quantity is increasing. So it means cost is increasing as quantity is increasing. Which cost is increasing as quantity is increasing? I can see this one, right? Why? Because this holding cost is directly proportional to this quantity Q. And I can say it as it is directly proportional. I can say it is Y is equal to some MX, right? That's it. Simply, I can say it is this curve. So I can say that this curve P2 represents the holding cost. I can say this is P2, curve P2. Okay, let me write curve P2. Curve P2, right? And ordering cost, you see, it is inversely proportional. the ordering cost is inversely proportional to the quantity Q. Hence, I can say this one is which curve? I guess you already know, because you see initially the cost is high and slowly as the quantity is increasing, the cost is getting reduced, and obviously it is curve P3. And also we know that the total cost represents this curve P1. We have already seen when we are drawing this, this cost plus this cost will give rise to P1. And I can say this is total cost. Good. And you might wonder, what is this P4? So let's go to the options. So in option number 1, what is given? Curve P1 represents total cost. Yes, it is true here. That is what is showing here. Curve P2 represents holding cost, right? And obviously what we have written is right. Curve P3 is representing the ordering cost, and there is another name for this also, and that name is setup cost. So we can say ordering cost, we say right, ordering cost or setup cost, right? So obviously P3 is, and P4 is production cost. What is this production cost? Production cost is nothing but the number of quantity that has to be produced. So the production cost will not depend upon the quantity Q. The production cost will depend upon the demand. So whatever you are trying to demand, it will be depending upon the demand. It is not on the Q, right? So that's the reason why you can say curve P4 represents the production cost. And that's a very simple question and a very easy question. I hope everyone might have answered this right. Good. Now, this is the right answer. Next. Okay, let me tick it rather than circling it. Right answer. Good. Now, let's proceed. So, in the second question, they've asked, when here I have taken the question paper and so the numbers will match with the online question paper that GATE committee has released. So this is our first question, and the second question belongs to, again, it belongs to this operations research. In operations research, it is coming under shading. The directions are important. If you know the directions, if you're shading properly, you'll get the region, and you can tick the region and go to the next question. No need to solve this question. Okay, that's a very good thing. It's a simple question, obviously. So let's plot this aside and we'll see what is happening. Okay. So what is given? Some objective maximization function. No need of that objective function. We do not care about objective function also. We have to only consider about constraints. Only constraints are important for this question, because there is no need to calculate anything, right? So they're asking what is the feasible region. That's it. The feasible region will depend upon constraints. Okay. So what are the constraints here? The constraints here are these four. These four are constraints. Subjected to will write constraints. Good. Now let's draw the plot here, the side way, and discuss what's happening here. So let's take same thing. Okay, let's go for different color here. Okay, good. This is this, right? And this is x1, this is x2. Good. Now we will plot each one of it. So before plotting, let's make some markings. Let's better make some markings. So I'll make some markings like maybe 20, 40, right? 60, 80. What is the maximum? Oh, it went to 600. Okay, it might not go till that point. Okay, 20, 40, 60, 80, 100, 120, right? And here also we can go for like this: 20, 40, 60, 80, 100, 120, so 140, something like that. Okay, so now let's plot whatever it is. See, the first one is x1 less than 45. What is 45 here? So let me take some curve here. So x1 45. So it should not cross 40. So this is 20, 40, and this is 60. So I'll draw some line here as 45. So let me draw a line at 45. This is 45. So maybe something like this. Okay, I don't know. Okay, this is 45, right? And x2 50. So this is 20, 40, and this is 50. And both are having less than or equal to symbol. Less than or equal to symbol in the sense we have to shade towards the origin, because x1, if you put x1 as 0, origin, right? This is origin 0 comma 0, right? 0 comma 0, right? If you are substituting this value into the equation, into the constraints, you'll have 0. 0 less than 45, true. So you have to shade towards the origin. 0 less than 50, yes, that's also true. You have to shade towards the origin. That is what is the trick that we have developed, right? Good. Now, let's shade it towards the origin. So as it is a little tricky, so I'll just make something like this. I'll make something like this where it will tell you the direction in which it has been shaded. So this direction we have shaded. This direction we have shaded. Here also we have shaded in this direction. Sorry. In this direction, here also we have shaded in this direction. In the sense, this is the common region. This is the common region for these two curves. Good. For those two lines. Now for the next one, in which direction 10x1 plus 10x2 greater than 600. Now you have to see if x is equal to 0, what is happening. If y is equal to 0, y is x2 is, if x1 is equal to 0, what is happening? It is if x, okay, what I'm saying is that for this equation, if you want to see or if you want to draw the constraint line, what is that? You have to make equal to constraint and draw, and then you have to draw the shading. Good. Here, if x1 is equal to 0, x2 is equal to 60. x2 is equal to 0, x1 is equal to 60. So the point is 60 comma 0 and 0 comma 60. So this is one point and this is another point, right? This is one point and this is another point. You have to shade that too. So let's shade that. I mean, you have to draw the line first and then you have to shade it. So this is the line. In which direction you have to shade? In which direction you have to shade? Just substitute 0 comma 0 in this. If you are substituting 0 comma 0, this 0 comma 0 in the constraint that I'm showing here, if it is satisfied, then you have to shade towards the origin. If it is not satisfied, you have to shade away from the origin. So if you see here, the substitute 0 comma 0, 0, 0, 0 greater than 600. That is not true. Obviously, you have to shade away from the origin. That is what you have to shade this side. You have to shade this side. You have to shade this side. Okay. Now, after this, now we have to do this. That is 20 by x1 plus 5x2. This thing. So if x1 is 0, x2 is some 250 around, right? Some 250 around. Because 75 divided by 750 divided by 5 will be 250. So it will be what? 0 comma 250 somewhere, you can take 250 somewhere there. And x20, x1 will be 750 divided by 25. That is approximately 25, 50, maybe some 50, right? So 50 comma 0. So 0 comma some high value and 50 comma 0. So somewhere it will be there. So let me draw this line here. So somewhere it will start here. And here it is, this is 40 and this is 50. Something like this. Just give me, this is 40, this is 50. Give me 1 minute. 25 comma this thing, right? Okay. Somewhere like this. So 25, 25. Okay. Somewhere like this. Okay. Now you have to shade this side. Which side? If it is satisfying 0 comma 0, you have to shade in the direction of origin. If it is not satisfying, away from the origin. As it is satisfying, you have to draw, you have to shade in the direction only, in this direction only. Now see, what is the common region here? Now see, what is the common region here? The common region you should be able to identify. So what is the common region here? If you are identifying, the common region is this, simply this. Okay, so that is what is your region Q. That is what is your feasible region. That is what is your feasible region. That's it. It's a very simple question. The answer is B. Very, very, very simple question. Okay, it's very easy one. Good. Now, let's go to the next question. So yeah, and this is one of the good questions. We have already discussed this in our topic in our class also. This belongs to 3-to-1 principle. So we have seen what is 3-to-1 principle, and when we're discussing about jigs, fixtures, and also principle of location, right? There we have discussed this. So it's a simple question. Let's read the question and understand what is that answer is. So what is that? A cuboidal part has been accurately positioned first, arresting 6 degrees of freedom, and then clamped in a fixture to be used for machining, right? So clamping, fixtures, right? Locating pins in the form of cylinders with hemispherical tips are placed on the fixture position. 4 different configurations of locations have shown. Which one of the following is correct? Good. So if you remember the principle, what was the principle of location? The principle of location or you can say 3-to-1 principle of location. We have discussed. What was it? We'll put 3 pins at the bottom, 2 pins to the perpendicular to the bottom, and 1 pin which are perpendicular to the previous 2 planes, right? So that was 3-to-1 were the pins. So in these diagrams, can you see in which configuration can you see 3-to-1, and all the pins are like these 3 pins, 2 pins, and 1 pin placed on mutually perpendicular planes. This is what we have seen, right? Good. So if you see here, these are the mutually perpendicular planes. So you can see bottom, this side, bottom side, and this side. Same way, this side, and this side. Everything is same, right? Now what I can say, let's see the options. What are they asking? Configuration P1 arrests 6 degrees of freedom, while configuration P2 and P4 are over constrained, and configuration P3 is under constraint. So like what they are saying is that which configuration is over constrained, which configuration is arresting 6 degrees of freedom, and which configuration is under constraint. What is over constraint? Over constraint means putting the number of pins more than what is required. Under constraint means putting less number of pins which are required. Over constraint means you are putting more. Let us say if 2 are required, you are putting 3. Over constraint. If under constraint you want 3, you are putting only 2, then it is called under constraint. So based on this, we can try to match the options. Before going to the options, we will see which is over constraint, which is under constraint, and then we'll pick the solution. That's it, right? So the first one, P1 configuration. In P1 configuration, if you see here, the 3 prints are putting here. So what are the degrees of freedom here? What are the degrees of freedom that you're trying to arrest? That is very important. So there are how many degrees of freedom, right? So you have less, right? 3 degrees. This mutually perpendicular axis X, Y, right, and Z, right? So you have plus X plus Y plus X minus X plus Y minus Y plus Z minus Z, counterclockwise rotation of X, clockwise rotation of X, counterclockwise rotation of Y, clockwise rotation of Y, counterclockwise rotation of Z, clockwise rotation of Z. Like that, you have 6 plus 6, 12 degrees of freedom, right? So if what if you don't have any constraint, it is floating in air, it is having 12 degrees of freedom. Now if you're putting 3 pins at the bottom of your cuboid part here, what is happening? You can't go. So okay, let's do this. Let's do the count. How many degrees of freedom it is constrained. So just assume this configuration, I mean this matchup here, in the sense what I'm saying, the coordinate system. So here I can say this is like this. So this is Z, X, and Y. If you're putting from bottom, so you're putting towards the positive Y direction, you're pointing towards the positive Y direction. So you can't go in the negative direction. So negative Y is constrained. Okay, let me write it like this. Here, negative Y is constrained, right? And what is constrained? Negative Y you can't go down, right? That's it. And can you rotate? Can you rotate along this direction? What do you mean? Uh, so this side, of course, here you can see here you have put it along a positive X, so negative X you can't go, right? And here you can see you can't go in the direction of negative Z, right? You can't rotate along the right positive X positive clockwise direction of X you can't rotate, clockwise direction of X you can't rotate, right? Clockwise direction of Y you can't rotate, right? Clockwise direction of Y you can't rotate, and of course clockwise rotation of Z also is not rotated. I think here what they have taken, instead of having the rotations in 2 different directions, they have taken only 1. That's the reason. Right? Actually, it should be 9, but they've given 6 in the sense they are assuming it to be rotations are counterclockwise or clockwise. They are taking it to be same. Okay. So I repeat, we have positive X and Y, positive X and Y, positive Z, and only rotations of X, Y, Z. Right. So it means that 1, 2, 3, 4, 5, 6, 7, 8, 9. Out of 9, 3 are obviously, 6 are obviously constrained. Right. So now in the same way here, oh, you see here, there is one more pin extra added. There is no point. There is no need of it. Actually, 3 are sufficient enough for that. So that's the reason why P2 is over constrained. Right. P2 is over constrained. Over constrained. Right. And you have, okay, you see there is one more pin missing here. There is one more pin missing either here or here. You can put one more pin is missing. So this is under constraint. Under constraint. Right. And P4, again, P4 is over constraint. Over constraint. Because you have 4 pins. No need, 3 are enough. Over constraint. That's it. Now let's go to the options and see what is right. So they're saying that P1 configuration arrests 60 degrees of freedom. Yes, you're right. While P2 and P4 are over constraints. Excellent. And then configuration P2 is under constraint. And that's it. This is the answer. This is the answer. No need to think any second thought is not there. This is the answer. Right? So you can say that. So let's remove this thing. Simply without knowing all this stuff also you can just say, by looking at the pins you can say which is over constraint, which is under constraint. Forget about the 6 degrees of freedom, but which is over constraint, which is under constraint. Happily we can say without calculating how many degrees of freedom is been arrested by P1, P2, P3, P4. Simply we can say it. Very good. It's an easy question. I hope who have attempted, whoever knows the concept might have attempted very easily. Good. Next. 2 surfaces. So this is from welding. Right? So what is that? This is also easy question. 2 surfaces P and Q are being joined in which of given joining operations there is no melting of surfaces P. Oh, it's a very easy question. What is that? They're saying that which one of the processes is not having melting in the process. Melting means you have base metals P and Q. So let's say you have some this P and you're joining with something like this. Right? So you're joining some welding is being done here, right? So let's say this is P and this is Q. So now if they have to be joined, They are saying that in which of the process there is no melting between P and Q, right? Obviously, in arc welding, melting will be there. So this is not the answer, because in arc welding you have this terminals. You have to close the circuit, and electricity is passed. You have some kind of electrode. All these things are there. So obviously P and Q will be melt. So this is not the answer. Brazing, yeah, this might be the answer. Why this can be the answer? Because brazing, what we do, we clean the surface by using some surface process. We'll remove that. We'll apply this borax and all, right? And then after that, after cleaning, just you put the brazing content there, where you have that solder or brazing content. You put it, because of capillary action, it will suck. So there is no melting of P and Q. So obviously this can be the answer, and this will be the answer. Brazing is answer, and there might be one or more options. Obviously, we have to check that. Adhesive also is one of the options. Why? Because you're not melting anything. You are just putting some adhesive between two joining mates, and then you're just sticking them together. That's it. You're getting the joint. Spot welding, obviously, you have to have melting. Why? Because if you have spot welding, you have plates like this. Remember, you have plates like this. At this junction, this is called your nugget, right? Nugget. So that nugget will be formed because of melting. Obviously, this will not be the answer. So I can say B and C will be the answer. Good. Next. This is from casting. In a metal casting process, to manufacture parts, both patterns and mold provide shape by indicating where material should not go. Okay, they are saying that some statement like where the material should go, material should not go. Which one of the following options given correctly describes the mold and the pattern? So we'll see which one of the following is correct. Mold walls indicate boundaries within which the mold part material is allowed. So just read carefully. Mold walls. So these are the mold walls. Mold walls are what? You ram it, you remove it, remove the pattern. After removing the pattern, these are the mold walls. Indicates the boundary within which molten part is allowed. Obviously, this is true. This is true because mold walls are there. In mold walls, see, you have some kind of sprue like this, and then you have here pouring like this, right? This is skim bob and all. I'm just skipping that skim bob. So, and this is your riser, right? This is your this thing. So if nothing has been poured here, nothing has been poured, right? Nothing has been poured. Obviously, this is your mold wall, right? Mold wall, and you're pouring liquid metal. Obviously, there is the contact. Good, very good. While pattern walls indicate boundaries of region where mold material is not allowed. Well, pattern walls indicate boundaries of region where mold material is not allowed. Obviously, right? Obviously, this is not true, right? This is not true. This is not true, right? So this is not true. Good. Next, molds can be used to make patterns. Molds can be used. This is a very tricky thing. This is a very tricky thing. What they're saying, molds can be used. Generally, we know that, okay, you can see the option. Patterns can be used to make molds. This is true. Absolutely true. But people get often confused with these things. Molds can be used to make patterns. So people will think that, no, it is reverse, right? So why we are thinking why molds will make patterns? Yes. If we can think of an example, we have discussed in our class. There is one technique where we will make the patterns using some molding technology, and then we use that pattern to make the mold again. What was that? If you remember, the example for this one was investment casting, right? Investment casting. We have injected the wax into a metallic mold, and then we solidify that, right? And then you take that wax pattern, then you coat it, you get the shell, and that is again a mold, right? By dewaxing it, you'll get a mold, and then you pour it. So this is also a right one. Next, pattern walls indicate boundaries within which molten material is allowed. Indicate this. Okay, this is true. While mold walls indicate boundaries of region where mold materials is not allowed. Okay, so here this second statement is little tricky. What is that? First statement is true. Patterns indicate the boundaries where which modern material is allowed. That's true. That's true. Here we told it's not true. Obviously, this is true. This is true. Pattern materials also should be in contact. It's allowed. It's allowed. It's allowed. While mold walls indicate boundaries of region where mold material is not allowed. So they're asking why this mold material. So people often get confused. Not allowed. It should be allowed actually, but there might be a reason. What can be the reason? Maybe they have coated. Maybe they applied some mold wash here. Right? They have applied some mold wash before pouring the liquid metal. They might have applied some mold wash. Right? The carbonious materials that we apply. Right? Mold wash. Right? This mold wash is applied. Some sand, some kind of material will be applying. Carbonious material. So when you pour, after pouring, there is some kind of a gas that is generated, and you can see there is a slight the mold material and the molten material. Mold material is this, molten liquid is this. So there might not be a chance in having contact between these two. So they're saying that they are not allowed means they don't want to have contact. So this can be an answer, but I'm not sure because what the statement of that statement that they have given as little ambiguous here. So if they are thinking about this mold wash, molding sand and all, and then this C is right. If they are not thinking about that, then C is wrong. So this is some kind of a question mark. Let's see and wait for the gate answer. If so, this is little ambiguous. Okay. If something is not clear, I think you can challenge them. Good. Okay. Next. Now let's go into the 2-mark questions. Till then we have discussed 1-mark questions. Now we are going to do the 2-mark questions. So in this, what they're asking, it's a simple metal cutting question, very easy. So in previous year also two, three times this question has come. We have even solved in the class also. Same thing, you have to apply the formula and get the answer. It's a very easy one. Here they have given the diagram also for us. Okay, very good. So what is that? In an ideal orthogonal cutting experiment, the cutting velocity, cutting speed is 1 meter. So let's write what is given. So given cutting velocity. So we can write, we have given as V, Vc, but we can write V also, right? They have given as V, we will write V. So it is 1 meter per second. And the rake angle of tool is given as this is 5 degree, right? And shear angle also is given is 45 degree. Applying the ideal orthogonal cutting model, consider 2 shear planes PQ, RS. Okay, they are saying this PQ and RS. Okay, this is PQ and this is RS. You can see the figure here. Close to each other as they approach thin shear zone. Shown in the thick line. So this thick line is thin shear zone. RS gets sheared. So R1, R2 to R1 shears to R2 and S1 to S2. So R1 to R2, S2 to. So this is a clear picture. We have already seen this thing. We have taken that and we have seen what is this. Generally we started with what is shear stress and shear strain. From there we have done in the derivation. If you have seen our notes, it will be clear, right? So assuming that the perpendicular distance between PQ and RS is delta. So you can see that the distance what they're talking about is this. The distance what they're talking about is this. That is what is that delta they're saying, right? So if you remember in our class, we have discussed that. So this is what is the shear. This is what is the shear that has occurred, right? This is what is the shear that has occurred. And that we have denoted as delta S, if you remember, right? And this delta, whatever the delta they have written, we have denoted it by delta Y, if you remember. That was the perpendicular distance, right? Then we have told that the shear strain or whatever it is delta S by Y. So let's write that shear strain is equal to shear that is happening divided by the perpendicular distance between these 2 planes, right? Good. So this is delta Y. This is what we have derived in our class, right? But they're not asking shear strain, they're asking shear strain rate, right? So shear strain rate, shear strain rate is equal to, rate means divided by time, right? So I can say delta S by delta Y by some time dt, small time, right? So I can write delta, I'll just manipulate these things by small time dt like this, I'll write, and divided by delta Y. Right? So here, instead of delta Y, they're writing as delta. So I can write that, I can write this as uh, delta S by T. Okay, here again, the important point to be noted here, delta S by T was shear velocity. The shear happening in that direction divided by time will be shear velocity, Vs. So it is Vs by delta Y, or in our examination, in our question here, they have given as delta. So shear strain rate is Vs by delta. Now what is given? Cutting velocity is given, but we don't have Vs. So we have to find out Vs. How do you want to find out Vs? We have this velocity triangle that we have formed, if you remember, right? We have velocity triangle. So this was some V and cutting velocity V. This is chip velocity Vf, and this was shear velocity Vs. Remember, we have made some velocity triangle. After velocity triangle, we did some in between angles. We had shear angle and rake angle. All these things were there, right? So after that, we have derived the formula as like this, right? Vc by cos. Just see our notes, you'll get it. Alpha is equal to Vs by cos alpha is equal to Vf by sin alpha. We have derived this sin phi. Right? Now what do you want? So this Vc, instead of Vc, we have there here they're making it as V. Okay, good. Now we have been given with V. We want to find out Vs. Delta is already given. Delta is how much? Delta is how much? Delta is 25. Delta is 25 micrometer. Right? So delta is there, Vs you have to find. That's it. Find Vs. So how do you find Vs? Just equate these two. Right? So V is given. Vs is equal to V cos alpha divided by cos phi minus alpha. Alpha is there, phi is there, V is there. All are there. Vs can be found out. What is V? V was 1 meter per second. 1 cos. What was the alpha value? Alpha is 5. This is 45, right? So this is 5 degrees divided by cos into 45 minus 5. And we can say, if we calculate, I have already calculated here. So this will be 1.3 meter per second. This is 1.3 meter per second. Okay. Now, okay, somebody has already joined. I'm sorry, I'm not seeing it. Okay. Good. Next. Okay. Next. Next is we have to calculate we have to calculate the strain. What was that? Vs by delta y. Vs by delta y or Vs by delta. Right? So Vs or shear strain rate I can write as by delta. What was Vs? 1.3. And what was the delta value that they have given? What was the delta value that they have given? That is 25 microns, right? 25 micrometer. So that is 25 into 10 to the power of minus 6 meters. That is meter per second minus 6 meters. So I have the calculated value here. Shear strain is approximately 5.2 into 10 to the power of 4. So meter, so what is that unit? Meter per second here, right? Divided by meter, right? So meter gets cancelled, it will be second inverse. That's it. That's the answer. That is the answer. Okay, very good. Very good. Hope you got this answer in the examination. Now, next. Okay. Anyone? Okay. Next. Next is, this is another very good question. So we have in class also we have discussed that what will be the BLU. Clearly we have been discussing the BLU and all the stuff, if you remember, right? So what were those? In a CNC machine has one of its linear position axis as shown in the figure, consisting of a motor rotating a lead screw, which is in turn moving a nut horizontally on the table, which is mounted. So a motor is there, and then it is connected to a screw. That screw, this motor will rotate the screw. This screw will move the nut, and as the nut moves, the table also moves. That's it. That is what we have discussed in our class also, right? That we have stepper motor, and servo motor we have discussed. Okay. So the pitch of the screw is 5 mm, and the total horizontal traverse length of table is 100 mm. So let's write what is given. Is given, right? So they are saying the motor directly has rotation steps of 50, right? So number of steps, I'll write number of steps, ns is 50 per revolution. Okay. Next, what is the pitch of screw is given. Pitch of screw is 5 mm. Good. Next is table length, right? Table length is 100 mm. Wow, nice. Now what they're asking, what is the total number of controllable locations at which the table can be positioned on this axis? So this is the axis. Controllable position means one small rotation. Okay, what is happening? Let's discuss what is happening here. If you are sending a pulse, this is your pulse. If you are sending one pulse, we have discussed, this is the concept where we have discussed this thing, right? So if you are one pulse, this motor should rotate with some rotation. What was the rotation? Already, how many steps it is having? It is having 50 steps. 50 steps in one revolution. But for one pulse, it will rotate 1/50th revolution or 1/50th rotation. So for complete rotation, you have to give 50 pulses. Then only one full rotation it will go. But here we are sending only one pulse. Why? Basic length unit is related to one pulse. Okay. Okay. Fine. So 1/50th rotation. So 1/50th rotation multiplied by pitch will give you this stable moment, right? Because 1/50th rotation is rotating, and that rotation will convert it to the pitch, and then only this nut will move in the direction, right? So I can say here basic length unit BLU is equal to pitch into 1/50 rotations. Pitch P into 1 by, so this is pitch. This is pitch, and this is 1/50th rotation. So one pulse will give you how much? 0.1. Okay, let me write a little bigger. So I can write BLU is equal to 5 into 1/50 is equal to 0.1 mm. 0.1 mm. Right? So this is what is basic length. What is basic length? Again, I'm repeating. For one pulse, this table has moved 1.5 mm like this. So the table will be moved 1.5 mm for one pulse. That is what is the basic length unit. Okay. Now what they're asking, so this is one position, one controllable location. There we can control. Control means wherever you can stop. Tuck, it has moved. Tuck, it has moved. Tuck, it has moved. So how many controllable locations are possible in these things? What that they are asking? Because your total length is 100. In the total 100 length, 0.1 mm one controllable, 0.2 mm another controllable, 0.3 mm one more controllable, 0.4 mm one more controllable. So what I can say is that I can count how many pulses you are sending. That is what they're asking. They're asking how many pulses you have to send, because one pulse is one controllable movement or one controllable location. So to get to the point, I can say that one pulse is giving, we have seen that 0.1 mm of table rotation, table movement. So for 100 mm movement of table, how many pulses? That is what is your question, right? So I can say pulses or total number of controllable locations are nothing but simply you can divide 100 divided by 0.1 will give you 1000. So 1000 pulses are required for the table to move 100 mm. That is what is the question. Okay, the answer is C. Simple. Answer is C. Okay, good. Next. Next is from material science. Next is from material science. So this also in class we didn't discuss much, but we have given some idea about FCC, BCC, HCP, and all these things. But this time the GATE committee has seriously taken this, and it is not very difficult question. Rather, it is not. I mean, people do not expect material science question, but out of the blue they gave this material science question. Good, we can solve it easily. So let's see, solve the question. Okay, so what is given here? The atomic radius of hypothetical face-centered metal. So this is what is your face-centered material. So I can say this is what is your face-centered cube or face-centered structure of a material. Face-centered. So it in between one atom will be there here, and I just one atom. So at every face, one center atom will be there, and some atoms will be at the side. 1/4 of the atoms will be shared at the corners of this thing. Okay, so let us assume, so according to this, let's assume that this is, okay, let me write here, this is the side length of unit cell is A, and let's say the radius is R, radius of each atom is R. Okay, so let's find out the relation between A and R. Why, I'll tell you. Okay, let's find out the relation between A and R, because it is required. So this is what is the diagonal, sorry, this is what is the diagonal. So how many R's are here? One R here, one R, 2R, and 1R. So R plus 2R plus R is equal to, this is for unit cube A, and diagonal length will be √2A, right? So this will be √2A. So I can write like this as R plus 2R plus R is equal to √2A, right? So 4R is equal to √2A. So A is equal to 4 by √2 into A, that is 2 √2 into R. Sorry, this is R. 2 √2 into R. Okay. So let's write this as R because let's not get confused. R, this is R. A is equal to 2 √2 R. Now let's go to the question. So they gave some atomic radius of hypothetical face-centered cubic metal is atomic radius R is given, that is √2 by 10 nanometer. So nanometer, let's make everything into one what do you say unit. So nanometer we convert it to meters. So you have to put everything into meters now. So what is that? Nanometer converted into meters by 10 into 10 to the power of -9 meters. So I can write this 10 also goes as, so I can say 2 into 10 to the power of -10 meters. I can write like this because this 10 also has been added, summed up there, combined there. And atomic weight is how much is that atomic weight? 24.092 gram per mole, right? But in question they're asked for kg per meter cube. So let's convert this into kg. So that is 24.092 into 10 to the power of minus 3 kg per mole. So we have converted that also. And taking Avogadro number, n, Avogadro number is written by n, that is 6.023 into 10 to the power of 23 atom per mole. Atoms per mole, right? Now, density of metal, says this is a formula. Density of metal, there is a formula. Density of metal, there is a formula. The formula goes like this. NAV is average number of atoms in that cell or equivalent number of atoms in the cell or atoms in the cell. They'll say like that. Or number of atoms in unit cell. They'll say like this. Into atomic weight divided by Avogadro number into volume of unit cell. Volume of that unit cell. Right? So this is the formula. Now we apply this formula. What is that? Average number of atoms. This is where we have already, I told you in class also, you have to remember this basic stuff. Average number of atoms in BCC structure, average number of atoms in HCP structure, average number of atoms in FCC, average number of atoms in simple simple cubic structures, right? So here how many atoms? So if you see at corners, we have 8 corners. 8 corners are there. Into each corner is contributing 1/8 of atom, right? Plus there are how many faces? 1, 2, 3, 4, 5, 6 faces are there. 6 faces are contributing 1/2 of the atom. So what are the average? So this is NAV. I'm just calculating. So what is that? 8 into 1/8 is 1 plus 6 into 1/2 is 3. So total number of average number of atoms are 1/4. So 4. Sorry, not 1/4. I'm sorry, 4. So total number of atoms in this unit cube A is 4, and that is what is your NAP. Okay. So let's erase this and just write that as 4. 4 into atomic weight. What is atomic weight? Atomic weight is given here, that is 24.092 into 10 to the power of minus 3 divided by, I got exactly 5.2 I had in steel. What is that you're talking about, Anand? I got exactly 5.2 10 to the power of which question you're talking about? Anand? This one? Okay. Some, okay, I don't know. I got a chat here. Is it previous one or the present one? But anyways, I'm just proceeding. If you have any doubts, please put in the chat. Thank you. Okay. Okay, this one. Number of this thing. Avogadro number is 6.023 into 10 to the power of 23 atoms per mole into what is the volume of cube? Volume of cube is A cube. A cube. I'll write it A cube here. What is A cube? We'll calculate. A cube is A is what? Under root 2 root 2 R we have given here. So that is what. So I will write it here. A cube is equal to 2 root 2 R whole cube, right? That is 2 root 2. What is R? R was, we have done. It is under root 2 into 10 to the power of minus 10 meters whole cube. That is what is A cube. So let's write that. Okay, just please help myself in mute. Oh, sorry guys, let's proceed. So Yeah. So it was, we'll substitute a cube here, that is 4 into 24.092 into 10 to the power of minus 3 divided by 6.023 into 10 to the power of 23 into a cube is 2 root 2, sorry, 2 root 2. 2 root 2 into root 2 into 10 to the power of minus 10 whole cube. Calculation has to be done very perfect. If you do the calculation, you will get around 3013 point approximately 64, right? Obviously, they'll be having some range. Don't worry about the decimal points, but yeah, you have to make that kg per meter cube. So this is your density of, and this is your answer. This is your answer. That's it. 3013.64 approximately around that way. That answer. Okay, good. Now, next. Next is ha. See again. So we neglected material science. Most of us will be neglecting that, but the GATE committee has taken this thing very seriously, and that is where the people will get filtered. Okay, so it is high time that we have to concentrate on every topic now. So that is the importance of every topic now. So then we have to make ready for every topic. It's not like this weightage, that weightage. Did you see? There's a 2-mark question from material science here, and there is a 2-mark question from material. 4 marks from material science. Never it has been happened. This is the first time. So we have to prepare for material science also very seriously. Okay, fine. So this question also we can try to solve. This is a basic liver rule problem, but you have to understand the terminology here. So before going into the applying the liver rule, we have to understand the terminology. Without understanding the terminology, there is no point in solving this question. So what is this? This is an iron carbon diagram, obviously. So what they're saying here, a steel sample with 1.5 weight percentage carbon. So this is what they're saying, 1.5 weight percentage carbon at this point. At this point, this sample is there. Okay, so no other elongation. Okay, there is no alloy. Is slowly cooled from. So it is cooled from here to just below the eutectide. So it is cooled from here, and just cooled just below this line, Okay. A part of iron cementite phase diagram is shown in the figure. The ratio of pro-eutectoid cementite content to total cementite content in the microstructure that develops just below the eutectide temperature is. Okay, let me explain this question. Okay, what they are saying is, okay, there is one alloy sample at this percentage of carbon. They're slowly cooling, and just below this here. So what is this line? This line they're saying is as eutectide temperature line. So below that it is called eutectide. Okay. Now below that there will be some composition in the component. Actually, there will be some mix of gamma and mix of cementite will be there. Okay. Actually, this is gamma plus cementite. So it's called leduberite. If you go and see, it's called leduberite. Okay. So to terminology, so let's do terminology also here. Best, we'll do the terminology. Okay. So if you see here, this point is what is important. This point is what is important. Why it is important? Because that is where 0% of, that is where 100% of perlite is reaching to 100% of cementite or pro-eutectic cementite. So this is called perlite here. I'll write point as A. A is perlite, 100% perlite. I'll write some point B here. This is 100% pro-eutectic cementite. Cementite means Fe3C. Fe3C is called cementite. Pro-eutectic means higher level. Okay. So A is, I'll write 100% perlite. B is 100% pro-eutectic cementite. Cementite means, if it sometimes people even write Fe3C is cementite. more amount of carbon, high amount of carbon, very brittle in nature. Okay. So now they are having this composition at this, right, at this point, right. So and just below that point, just cool it. So what will you get at this point? This point you'll get a mixture of perlite and pro-eutectic cementite, right? Mixture of, because it is in between, cementite, or you can say mixture of perlite and pro-eutectic cementite. Okay, mixture of it. And let's denote that point. It's called fulcrum here because we want to calculate these ratios, right? It's called fulcrum in this case. The fulcrum here I'll just denote it by some P. Fulcrum I'll denote it by some small p. Now what they're asking, the ratio of pro-eutectite cementite content to the total cementite content in the microstructure. So in this thing, the ratio of pro-eutectic cementite is between A and B, right? And total cementite is between these 2 points. Here, I'll write it in different color. This is your basic ferrite, 0. This, let us say this is C, and this is your D, pro-eutectic cementite. And again, this is your fulcrum. Again, this is your fulcrum, and that is what is your Q. So the bottom line is for total, and top line is for the pro-eutectite cementite. Now we have to apply this rule, right? The fulcrum rule, right? So let's apply that. So mass fraction, or I can say the total proportion, I can say proportion or mass fraction, anything is fine. Mass fraction of pro-eutectic cementite. Let me denote that as F1. F1 is equal to, it is nothing but, so you want this value, I will go in different way, right? So that is what is AP divided by AB, AP divided by AB. So what is AP? AP is nothing but, what is that? 1.5 minus 0.8, right? So it is 1.5 percentage of carbon, 1.5 minus 0.8 AP divided by AB is 6.7 minus 0.8. So this F1 will, that fraction, mass fraction will be approximately, according to my calculation, it is 0.1186, something like that I'll get. Okay, let's calculate the fraction for the next total one, that is CQ divided by total CD, right? So I'll write here as, what was the ink I've taken? Okay, blue. So good. So the total mass fraction or mass fraction of total cementite is, let's say F2 is CQ, right? The CQ divided by CD, right? So what is that CQ? CQ is nothing but 1.5 minus 0.035, and CD is 6.7 minus 0.035, right? Is 1.5, lever rule. It's called lever rule. Fulcrum, right? Fulcrum is at Q here. 6.7 minus 0.035. So you'll get around 0.2198, something like that. So let's say this is F2. What is that they're asking? They're asking the ratio of pro-eutected cement content to total cemented content. So that is what they're asking. This F1 by F2 they're asking, and that is 0.01186 divided by 0.2198, and the answer would be approximately 0.54. That is the answer. So you have to fill the value as 0.54. Good. Now Now let's proceed to the next question. Let's proceed to the next question. That is this. Okay. So what they're asking there, the okay, the part, okay, I think yeah, the okay, okay, this is from the control charts, that is industrial engineering, right? So this is from the industrial engineering. Okay, fine. Now a part produced in high volumes is dimensioned as shown. The machining process making this part is known to be statically in control with based of sampling. The sampling data that D1 follows a normal distribution with mean of 20 and standard. So normal distribution. So obviously, it is kind of a bell curve distribution. So it's a bell curve, right? It's a bell curve, and the parameters of the distributions are mean and sigma. Mean is mu, and sigma is standard deviation. So now this D1 is following the mean normal distribution, as well as D2 also is following this dimension. D2 also is following the normal distribution, and they are having mean and mean value. Okay, what is given? Let's write what is given. So D1, they gave what is mean. Mean value they gave as 20 mm, and standard deviation sigma they gave as 0.3 mm, right? And D2 is having some mean of 35 mm, and this is 0.4 mm. Okay, good. So now let's do this. What is that? They're asking an inspection of dimension C is carried out in a sufficiently large number of parts to be considered on the Six Sigma process. Now, Six Sigma, what is Six Sigma? So this is normal distribution. So what if you are considering this as a normal distribution? So then just draw this graph like this. So this is some kind of a bell curve, normal curve, Gauss curve, everything is same, right? So this is your mean, mu. This line is mean, this line is mean, this line is mean, and this is your spread, that is standard deviation. This is minus 3 sigma, this is plus 3 sigma. So that is what the Six Sigma control process is meaning. So what is that? We'll see. Okay. Now they're asking upper dimension of C, because here this mean plus or minus 3 sigma is there. No. So they're asking the upper dimension. So let's go and discuss this now. Let's solve the problem. What is that? So here from this thing I can say D2 is equal to D1 plus C, or D. Okay, let me write. So average. So this is taken for so many sufficiently large parts. So many sufficiently large parts they have taken. So I'll write something. D2 bar. D2 bar means mean diameter is equal to D1 bar plus C bar. What is that? The mean diameter of D2 is equal to the mean diameter of D1 plus mean diameter of C. Okay. So from here I can say C bar is equal to D2 bar minus D1 bar. So what is mean? So this bar is nothing but mean. So the mean of D2 is how much? Mean of D2 is 35. Mean of D1 is 20, right? So mean of D2 is 35. Mean as D1 is 20. So here I can say C bar, the mean of C will be 15 mm. Good. Now I have to find out the standard deviations of C. I have to find out the standard deviation of C. So the can I do like this? So like adding means, we can't add means. In standard deviation, let's say standard deviation of this group is 1, standard deviation of this group is 2. The total standard deviation 3 is not sigma 1 plus sigma 2. This is wrong. So this is sigma 3 square is equal to sigma 1 square plus sigma 2 square. So you have to square them. That is important. Okay. So let's go here. let's go here. So let's find out this thing. So I can say sigma d2 square is equal to sigma d1 square plus sigma c square. So standard deviation of d2 is equal to square is equal to standard deviation of d1 square plus standard deviation c square. So that is what I've done. So we have the values of these things also, right? So standard deviation of d2 is how much? Okay, we want sigma c square, right? So this is what is sigma d2 square plus sigma d1 square is equal to, sorry, minus how much is that? So you can just write it is d2 is 0.4, so 0.4 square minus 0.3 whole square. I have the value is 0.007, some value that. Now we have the standard deviation of okay, we didn't have, okay, we have to find out. So here sigma c is equal to under root 0.07. Okay, now we can find out the upper limit of dimension c. So upper limit of dimension c, people even write as UL, upper limit of dimension c is equal to c bar plus this z into sigma c. What is the z? That is what is 6. In this case, it is 6 sigma, right? C bar is 15 hour in this case, plus z is 6 sigma. So let me write not z, I'll write sigma only, 6 only. Let's not worry it, 6 sigma, right? 6, right? 6 into this is under root 0.07, and this is approximately I'll get 16.587 mm. So this is the answer for this question. Okay, good. Anyone who is having any doubt here? Is it clear? Hope it is clear. Okay, now let's go to the next question. That is, this is on additive manufacturing. And this is also a, even though you have to know some basic understanding of additive manufacturing, but there is no need to have an idea of solving this question previously. It means that you don't need to see this kind of a question before itself. Directly in examination, you can try to solve if you have some basic intuition. If you have some basic intuition, you would have answered this question very, very easily. But rather than, this is one kind of a question that has been asked in additive manufacturing. So let's solve this question. So what they have given here, solid part of polymer material is to be fabricated by additive manufacturing in a square shaped layers starting from bottom of the part working upwards. The nozzle diameter of additive manufacturing machine is A by 10. So nozzle diameter given is A by 10. Some A is some value, A by 10, what is that? Mm. And the nozzle follows a linear serpentine path. There's a path planning for additive manufacturing. Serpentine path parallel to the slices of squares layers with a feed rate of A by 5 mm per minute. So feed rate F is equal to A by 5 mm per minute. A by 5 mm per minute. Now, ignore any tool path motions other than this, whatever they are saying. Time taken to fabricate. Simple question actually. See, there is no need to understand 3D printing much. Basic understanding of 3D printing is enough. How 3D printing is done? So first, you'll do this layer, then this layer, then this layer, this layer, this layer, this layer, this layer, then this layer, this layer, this layer, this layer, this layer, then this layer, this layer, this, like this you'll do from bottom to top, layer by layer. You'll go keep on printing with that nozzle. So there is one nozzle and some extrusion, some kind of liquid metal or something like that is falling, and then you can like a serpentine path. Maybe this is the path they're using, like this. They'll deposit, and layer by layer, they'll try to deposit. That is what is additive manufacturing, right? So now what they are asking is, what is the time taken to fabricate? Simple question. Time taken means what? What is the information given here? Diameter of nozzle is given, feed rate is given, and dimensions of the part also have been given. So if you want to find out time taken, so in casting, if you have seen in metal casting, we have seen that. So let's calculate first the volume, because volume is important, right? So let's calculate the volume. So volume of part, right? So I'll write here as 1, 2, and 3, because 3 sections are there. 3 sections, V1, V2, V3. So volume of part is equal to V1 plus V2 plus V3. Okay. So what is V1? V1 is equal to 3A into 3A into 1.5A. 3A into 3A into 1.5A. What is that? 3 threes are 9. 9 threes, 9 1.5s. 15 nines is 135. So on 13.5 A cube. Right? V2 is 2A into 2A into A, because width, length, and height. A is equal to, it is simply 2 to the 4, 4A cube. And V3 is A into 5.5A. So A into 0.5A, that is 0.5A cube. So total volume, let's add total volume. V is equal to V1 plus V2 plus V3, and that is what is 13.5 plus 4 plus 0.5. So that is 13.5 A cube plus 4A cube plus 0.5 A cube, right? And you'll, I think you'll get around approximately, this is 14, 18 A cube. Okay, that's it. Now we have the total volume, but we want time. And if you see, they have given the feed rate and diameter of nozzle. So the diameter is this much, and from that diameter of nozzle, this feed is coming by A by 5 mm per minute. That feed is coming. That at that rate, that material is dropping onto the part. Okay, so I can say volume flow rate can be calculated. How volume flow rate? What is volume flow rate? What is volume flow rate of that? Volume flow rate of discharge metal, or I can say discharge of metal. How much metal is falling? How much metal is falling? So that volume is having some nozzle. In that nozzle, we have some, in casting also we have done, if you remember, that area is there. What was the nozzle area? Nozzle area will be pi by 4 d square. That will be the area of cross section into feed rate. What was the feed rate? There we have considered velocity. A into V is discharge, if you remember. Here A into feed rate in velocity only. Feed rate is F. So it is pi by 4. So this is what? This is area of cross section of nozzle entry, right? So pi by 4 d square into feed rate was A by 5. So this D is nothing but D nozzle. So let's do that. So pi by 4 into D nozzle is how much? D nozzle is A by 10. A by 10 whole square plus into A by 5. So this will come around okay, fine, you can calculate. I think I have some value, that is 1.57 into 10 to the power of minus 3 A cube. What is the unit? Here? mm square, cube per second or per minute. What is that they have given? Per minute. Oh, this is per minute. So cube per minute. Okay. So what is time required now? We have in casting also we have seen time required total time required of filling, if you remember, that was what? If you remember, what was that? Volume of the casting, that is what we have to fill, divided by the discharge, same thing. So total volume by discharge. What was the total volume? 18A cube divided by 1.57 into 10 to the power of minus 3A cube. This gets cancelled. You get around 11465 minutes. This is the answer. This is the answer for this question. Okay. So now let's go to the next question. See. So till now in metrology, they were asking only, that what was the upper limit of these fit, interference fit, tolerance fit, that tolerances, fits tolerances and all this were asking. But they have asked some different question, that too on optical, flat and fringes, they have asked this, right? So it means that again, it's important to read everything with equal importance. With equal importance, we have to read, and then only we'll be able to crack it very nicely with good rank. Okay, so let's read this question. This is a simple question actually. If you know the formula, you can easily apply. If you do not know the formula, there is no point in doing this question. Okay, the formula is very simple. We'll discuss this. What is that? An optical flat is used to measure the height difference between a reference slip gauge A and a slip gauge B. So this is a slip gauge A. You can see here. This is a slip gauge A here, and this is a slip gauge B here. Upon viewing via the optical flat using monochromatic light of 0.5 micrometer. So they have given the value given, that is wavelength. Wavelength is denoted by lambda, that is 0.5 micrometer. Right? 12 fringes were observed over a length of 15 mm of gauges. So fringes, number of fringes, how many of the number of fringes? See, say some light is coming, then you are observing some fringes here, so like that. Okay, so fringes, number of fringes are 12 per 15 mm. Okay, fine. So 12 per 15 mm. Now wavelength lambda is given already. Fringes were observed over a length of 15 mm of gauge B. On gauge B, we have seen. Okay. If gauges are placed 45 millimeters apart, so these are 45 meters apart, right? So distance between gauges is equal to 45 mm. Distance between gauges is 45 mm. Okay, so now they're asking the height difference between the gauges. So what are they asking? They're asking the height difference between the gauges. Okay, let's go here, take this. So that is what they're asking. That is what they're asking. So let's say that height difference is denoted by some delta H. Okay. So the formula is this. Delta H formula is this. Simple formula is n lambda divided by 2 into G by L. This is the formula. So what is this n, lambda, G? All are given actually. So lambda is given already. N are nothing but number of fringes. So this is n, right? This is the n. And the length is nothing but this length is L. And the distance between gauges is G. That's it. Simple formula. What is that? Number of fringes into wavelength divided by 2 into fringes per length. That length is L. G is the distance between the two gauges. That's it. Apply the formula, you get the answer. That is 12 fringes into wavelength is 0.5 micrometer. But here all are given in mm. So let's convert into mm. 0.5 mm can be converted into, if you multiply with 10 to the power of minus 3, then you will get it as 0.5 micrometer is there. If you're multiplying with 0, 10 to the power of minus 3, you will get it as in mm. Okay, into okay, divided by 2 into 45 is g divided by 50. If you do the calculation, you get approximately 0.009 mm, and you convert into micrometer, it is nothing but 9 micrometer. The answer is 9 micrometer. So this is from the metrology and inspection. The next one is the next one and the last one for our section 4 is this. That is simple question. When we are discussing metal forming, we have discussed this, that we have clearly derived at ultimate stress what is happening. All these things we have derived. So let's go to the solution. What is that? Ignoring a small elastic region, true stress and true strain variation of material beyond, right, yielding follows an equation sigma is equal to this thing. So what is given? Sigma is equal to 400 epsilon to the power of 0.3 megapascal. But this is which stress strain? True. So hence I'll write as sigma t epsilon t. The engineering ultimate tensile strength value. They are asking engineering. That is very important. People will forget. Aram se they'll write some answer. It is easy question they'll write, but that is where people will make mistake in hurry. Engineering they're asking, but the diagram isn't true. So if you remember, we have seen that if there is a graph like this in true stress strain curve after the elastic limit, if you see, so we have seen that, right? Something like this. So this is your ultimate point, right? At ultimate point, I told you strain hardening or strain hardening exponent is equal to true strain, right? N is equal to epsilon t. We have discussed this. This is ultimate point. Ultimate stress point. We have discussed, we have derived also this thing. How n is equal to epsilon, we have even derived it. Okay. So at ultimate stress point, right, we have this thing. So I can say at ultimate stress point, we have strain hardening exponent is T. But they're asking ultimate tensile strength value of the material is. Okay. So strength we want, right? So sigma T is nothing but we have the formula, that is into, see here the value of this thing is what? 0.3, right? So 0.3 already it is 0.3 to the power of 0.3 because n is 0.3 here, because this is n here, this is n, right? So simply calculate the value, you'll get it as 278.74 megapascal, right? Next is true strain, right? So now they're asking, this is what? This is ultimate tensile true strength. I want engineering strength. I want engineering. So I'll write engineering or here engineering ultimate tensile strength is nothing but sigma, I'll write it as like this, is equal to sigma t by 1 plus epsilon, right? 1 plus epsilon. But this epsilon is again engineering. Okay, this epsilon is again engineering. That you should not forget. Okay, so let's find out that. You know that true strain is equal to ln 1 plus engineering strain. So this is 0.3 is equal to ln 1 plus this thing. So ln 1 plus engineering strain is e to the power of 0.3. E to the power of 0.3 is 1.35 something. Let us substitute here. So this thing is sigma t, that is 278.35, and hence answer is 206. Here epsilon t are true and E and sigma are engineering. And if you remember, this also we have derived. How these values are coming, we have, these are the formulas, we have derived this also, if you remember. Okay, so that's it, guys. So that are the that is the manufacturing and industrial materials manufacturing industrial part for our GATE 2023 solutions. Hope I did not miss anything and everything I have covered. If I miss anything, please do comment in the chat box. I'll be able to cover it. Thank you, guys. If you have any doubts, please let me know. I'm here.